Welcome everyone to your second milestone project. In this section of the course, since you've learned about object-oriented programming, we're going to test your new skills with another milestone project. Just like we had a milestone project after learning about functions, we now have one after learning about OOP. But first, just like the last milestone project, to warm up, we're first going to guide you through creating a simple card game, and then you're going to attempt to actually complete the second milestone project exercise. So let's talk about your warm-up project, which is just a guided code-along project. To warm up for that second milestone project, we're going to recreate the card game called War, and we're going to do it together in a code-along. Let me have a quick overview of how this game works in case you haven't heard about it. But in case you have heard about it or just need a quick refresher and rather read the rules rather than watch this, you can just check out this Wikipedia link on the actual card game. But as a quick brief overview of how the game War works and how we're going to program it, we essentially start off with a 52 card deck, and then after shuffling the deck, we split it up into two decks. So half goes to one player, half goes to the second player. And now these two players will grab one of their cards and lay it on the table. So for example, we have Jack versus a King. And the card that has the higher ranking wins. And when a player wins this matchup, they take both cards and they go into their deck. And the player that loses is the one that has no more cards remaining. Now there is a caveat here, and that's when you pull out the cards and they happen to be of the exact same value. So here player 1 and player 2 have both pulled out a Jack, and those are equal to each other. This is an instance of war, and that's where the card game gets its name from. So in a war situation, we'll go ahead and then take out an additional set of cards, and this varies depending on what variation you're playing. Some people take out 3 cards, some people take out an extra 5 cards, but essentially the point being is you're going to take out an extra set of cards and set aside along with those matching jacks, and then you pull out a new set of cards. So here, now drawing again from their decks, player 1 now pulls out a Jack, player 2 now pulls out a King, King wins again, and now player 2 has won the war, and so they get all those cards passed into their deck. And these cycles end up repeating over and over again, a one-to-one comparison of cards, and if they happen to be equal, then you get a war, which means you draw another set of cards, basically a pile of 3 for each, and then you draw again. So when you win a war, you win a lot more cards. And this continues until some player has all the cards. So in this case, player 2 has, in theory, 1. Okay, so like I mentioned, that war process can be repeated as many times as necessary in case of back-to-back ties. So you can have like a double war or a triple war. Now to construct this game, what we're going to do is use Python's object-oriented programming. And we're also going to be exploring how classes can actually be connected to other classes, not just through something like inheritance. So we're going to start off with a card class, which is going to just hold the entities or attributes of a single card, like its suit, rank, and value. And then we'll have a deck class, which is actually constructed using instances of the card class. And then what we're going to do is also create a player class that can then hold cards or hold half a deck of cards. And then finally, and this is actually usually the hardest part, is construct these classes in a way and create instances of these classes in a way where we can actually perform the game logic. And in our case, we're not actually going to have a human player. Instead, we're going to just be simulating a game of war between 2 computer players. So the actual playing will happen between 2 virtual agents. All right, let's go ahead and get started. I'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to begin by creating the card class, as well as some global variables that will be used throughout the project. Let's head to a notebook and get started. All right, here I am at the Jupyter Notebook. Before we begin actually coding anything, I just want to briefly sketch out the logic of what we're going to be doing. So we're going to create a card class, and that card class should essentially just have 3 main properties. It should be able to understand the suit of the card, whether it's hearts, diamonds, spades, clubs. It should be able to understand the rank of the card, 2, 3, 4, 5, all the way to Jack, Queen, King, and so on. And then corresponding to that rank, there should also be an easy-to-use integer value. So that way, later on, when I'm comparing one card class to another, or one instance of a card class to another instance, if it's Jack versus Queen, I can simply use the value of something like 11 versus 12, or some sort of integer, in order to quickly decide which card has the higher value. So what we're going to do here is we'll go ahead and create the card class, and then in the next series of lectures, we will create a deck class, which is essentially the 52 unique card classes that come within a deck. So we'll show you in the next lecture how to generate a deck. And then after that, we'll create a player who can then hold cards from a deck. And then we'll start the game logic. But let's start with the first step, which is creating that card class. And this one actually requires us to create a couple of global variables that will be easy to use later on, especially when we create the actual deck. But what I'm going to do first is create the card class. I'm just going to call it card. And then you can use open and close parentheses here. They aren't necessary since we won't be using inheritance at all. Then we'll say def, and we have the instantiation method. Always remember it's double underscores here, so one underscore, another one. We always use self as the self-reference keyword here. And then what I'm going to do is when someone creates a card, what they should be able to provide is the suit of that card and the rank of the card. As far as the value, we don't need the user to actually provide a value because we'll figure that out automatically based off a dictionary of values that we'll create later on. So when you create a card, you give it the suit and the rank. So we'll say self.suit is equal to suit, and then self.rank is equal to rank. And in a little bit, we'll figure out how to actually add in the value. The other method I'm going to provide here is a string method. Just for convenience, if I ever want to print out a card that's easy for a human to understand, I'll go ahead and create an underscore underscore str underscore underscore method or string method. And let's decide what do I actually want to print out if I were to print out an instance of a card class. I'll go ahead and return self rank, and then I will concatenate it with space of space, and then I will concatenate that with a string self.suit. So that basically assumes that suit and rank that I'm passing in are strings. So let's go ahead and run this, and let's create an example of what I would expect a card class to look like. So if I wanted to create the two of hearts as an instance of a card class, what would I need to provide? I would need to provide the suit, so that would be something like hearts. And then I would need to provide the rank, so I'll go ahead and provide this as 2. And now, if I have the 2 of hearts just like this, it's going to be an instance of the card class at some location in memory. So that's what we have here. Hey, it's an instance of the card class at this location in your memory. What happens if we print this out? Well, recall when you print something, it looks to what the string double underscore method returns, which in this case should be the rank of suit. So it says this is the 2 of hearts. Perfect. So I also have those attributes, which is the suit. And then if we say hearts here, the rank 2. Now, unfortunately for us, these are both strings. So it's going to be hard to compare one rank to another because I can't really compare the string 2 versus the string 3 directly. I'm going to need somehow to translate this 2 into the actual integer 2. And for that, I'm going to use a dictionary of values. So I'm going to copy and paste this from the actual lecture notebook, but just to give you an idea of what we're trying to do here, is I'm going to create a dictionary where the values will have something like 2 as the key, and then the integer value 2 as the actual corresponding value. So what I'll do here is instead of typing this out all manually, go ahead and open up this actual code along notebook and then copy and paste the dictionary that we have there for you. And it should look like this. Basically, 2 goes to 2, 3 goes to 3, 4 goes to 4, and so on. And then 10 goes to 10, Jack 11, 12. And in our game, we'll treat ace as the high. So you run that, and now, if I take a look at values, and I pass in the 2 of hearts rank, which recall is just this string 2, I should get back the corresponding value integer 2. So now when I run that, I get back 2. Now what's really cool about this is because we're actually defining this at a global level, it's not within a class or not within a function, what I should be able to do is use values within the card class itself. And typically, when you're defining things like a large global variable like this, you'll put it at the top of your script. So just for readability, I'm going to cut and paste this up here at the top. And then what we're going to do here is the actual value will then be an attribute. We'll say self.value is equal to values dictionary, and then we can pass in rank here. So why rank and not why self.rank? Well, it's because inside the instantiation method, we're actually already passing rank. So we expect the person to pass in a 2 or a 3. Also notice that we're expecting this person to pass it in exactly as shown here. We'll get an error, for example, if I said a lowercase t, because values only has this uppercase t. So keep that in mind, that when we're actually constructing many cards, we'll have to make sure that the key value corresponds exactly as shown here. So make sure you run the values dictionary. We will again redefine this card class, and then let's go ahead and now create, let's say, the 3 of clubs. So that's a card class. No, I don't need to actually provide value. It still only uses suit and rank. So we'll say this is the 3, and then we'll say, whoops, actually suit goes first. So we'll say clubs, and it's 3. Run that, and now if I say 3 of clubs, I should be able to see the suit is clubs. Now let's check out the rank is 3, and unlike before, we should now have value. So you run that, and now you get this integer value. And after you've run everything in a new cell, you should be able to hit tab here and see rank, suit, and value as the attributes. And that's essentially what we need for our card class. We have the suit, the rank, and importantly, we have values. So now, if I were to redefine 2 of hearts, let's go ahead and rename this. So run these cells again, print 2 of hearts, suit, rank, and now if I see over here, let me delete this cell, and now I should be able to actually perform a comparison like we would during the game. So I can take a 2 of hearts card's value and compare it, whether it's less than, greater than, or equal to the 3 of clubs value. So run that, and it looks like 2 of hearts is true, less than 3 of clubs.value. Keep in mind, I can't compare directly the card classes to each other because these are card classes. They're not actually integers. I would need to do it with the actual integer value here in order to get something that makes sense. And I can do things like check for equality, false, and I can already begin to see how the card game would work because I should do an equality check to make sure that we're actually not at an instance of war and drawing more cards. Okay, so that's basically it for our card class. Again, we have the provided suit, rank, and then we have this values lookup, which corresponds to this global variable. And you'll see that quite often in object-oriented programming, where a card class can reference either something like a global variable at the top or even an imported library. So for example, later on we'll see that I will import random, and then inside of this card class, because I imported random, I could do something like random shuffle, which we will actually use within the deck class to shuffle a deck. Now the last thing I want to do here is create 2 more objects that will be global variables, and that is a list of all the suits as well as a list of all the ranks. In fact, we can just make them tuples. So what I will do is I will copy and paste these from our solutions notebook or code along notebook. So here we have suits, hearts, diamonds, spades, clubs. It's going to be a tuple or list. I'll save it as a tuple just to kind of iterate that I don't really want to change this. And then we'll have ranks here. So I'm going to copy and paste this from the notebook. You can do the same, or you can manually type this out if you really want to. But here I'll have the ranks. And the reason I have the ranks and the suits is just to make sure everything is formatted correctly when we begin actually creating an entire deck. So what I could do is for every suit, create a ranked card class here. And I want to make sure that these ranks match up the strings exactly as the values here. So just go ahead and run that, and we'll be using these global variables in the next lecture when we create our deck class. And as I mentioned, something to keep in mind is because we're using this values global variable up here, and it relies on rank, that when I pass in this specific rank, it has to match up exactly as the key here. So if I were to do something like have a lowercase 3, for instance, you'll get an error because it says, hey, I can't find 3 as a key within this values dictionary, which makes sense because it's a capital 3. Same thing if you were to provide something like 3 here, run this, you'll get another key error. Now if you wanted to, you could just have the user or creation method or instantiation method also provide value instead of just suit and rank. But this method basically looks it up for you and makes sure that every instance of the card class is performed or created correctly. All right, so that's it for the card class. Simplest class we'll have in this project. It's just a suit, rank, and a corresponding value. Suit and rank, that really helps us if we want to print out the cards throughout the game, kind of show what each player has. And really, the workhorse here is going to be this value lookup. That's what's going to allow us to play the game logic. Okay, now that we have a single card class ready to go, we have to create a deck of cards for the players to split, shuffle, and play around with. So in the next lecture, we'll see how we can actually create instances of the card class within another class. I'll see you there. Welcome back, everyone. To continue on with this lecture series, it's time to create a deck class. Let's talk a little bit about what this deck class should be able to do. There's three main things that we want to achieve with this deck class. The first is whenever we create a deck class, we would like it to instantiate a new deck, which essentially means create all 52 required card objects and then hold them as a list of card objects. And this is something a little bit new that we haven't seen before, and that is to say that when we instantiate that new deck, we're not just creating something like a list of strings or a list of integers. Instead, as an attribute within the deck class is going to be a list of all the cards. And then each variable inside that list is actually representing a full card object, which means that card object has that suit, rank, and value that were created in the previous lecture. Next, we want to shuffle a deck through a method call. So after creating a deck of those 52 card objects, we want to be able to simply shuffle the deck to make sure they're in a random order. And we can do this with the random libraries shuffle function. And finally, we want to make sure we can deal cards from this deck object. So we know that the deck class is essentially holding 52 card objects at the beginning, and then if we want to deal cards from this deck object, we'll simply use the pop method to grab from the essentially top or bottom of the deck. So what we'll be seeing, and this is again the new part, is that the deck class holds a list of card objects. And we haven't seen this before in the lecture, so this is one that we're going to take a little bit of time with, and it's the fact that we have a class object using instances of another class as part of its attribute. So it's not really inheritance or anything like that, and it's not polymorphism. It's just the fact that instead of holding integers or strings, what we're doing is we're actually holding cards, and that is our specific card object. Okay, let's go ahead and get started to see how this all can be done. Okay, here I am back at my notebook. What I want to point out is at the top of this notebook, if we scroll all the way to the top, recall that we imported random, and then we also have the suits and possible ranks, and the corresponding values dictionary here. So if you want to follow along with me, you should have these 4 lines ready to go, as well as our updated instance of the card class that has the suit and rank, and then uses this values dictionary to look up the value based off the provided rank. So let's go ahead and rerun these just to make sure we have them ready to go. We can delete that purpose error that we saw in the previous lecture, and then I'll scroll down and begin creating my deck class. So we'll say class deck, up to you whether you want to put parentheses or not, they're not required. And then the instantiation method. So init underscore underscore, 2 underscores, and then the self keyword. And now what we want to do here is we want to create a deck. So what should a deck consist of? Well, it should be all 52 cards. And in this case, we want all 52 card objects. So the way I'm going to do this is I'm going to have an attribute called all cards. And note here that I'm not going to actually take in any user input because the user input isn't really required. Every deck or every new deck should be the same. So if I were to create a new instance of a deck, it should be exactly the same as the previous instance of a deck that I previously instantiated. So what that means is self all cards will start off as an empty list with no input from the user. And then what we'll do here is the following. I know I need to create essentially all 52 unique cards. So I'll say for suit in suits, and recall suits is that tuple that I have up here of hearts, diamonds, spades, and clubs. So for every suit, so for every heart, I need to create a rank, 2 of hearts, 3 of hearts, 4 of hearts. Then I need to do the same for diamonds, spades, and clubs. So what I'll do here is say for suits and suits, and then for rank in ranks, and this is where I will create the card object. Okay, so we'll be creating the card object here, which means I'll say self dot all cards, and I will append. And the reason I can call append here on all cards is because all cards right now is just a normal Python list, and that's how it will be. So what I need to do is say created card. And what is created card here? Well, let's create it. I'll say created card is equal to card, suit, and rank. And that will actually create a new deck for us. So what does this actually mean here? Well, I have this class deck. Upon creating a new deck, it creates a brand new empty list and then fills it up with all the required cards. So that's for suit and suits, essentially hearts, diamonds, spades, clubs. And then for each rank, it creates that card. And recall, each of these cards will then be unique because it's just a for loop through these. It doesn't repeat anything. And then we take that newly created card and we append it to the list of all cards. Let's make sure this works as expected. So let's create a brand new deck of 52 cards. Open close parentheses here, and there we go. So upon creating it, it should have already ran through this for loop. So let's say new deck and check out all cards. There we go. And so sometimes students get confused here. They expect to see something like 2 of hearts, 3 of hearts, and so on. But recall that all these things are actually card objects stored somewhere in memory. However, it is a list of them, and what we can do here is let's just grab the very first card in this list. So we have this card object, so we'll say this is the first card in this new deck, and if I take a look at first card now after running that cell, I should be able to see rank, suit, and value, which means since this is a card object, I can also print first card, and it reports back 2 of hearts. Now, is this what I expected? Well, if you scroll back up here, notice that hearts is the first suit, and then 2 is the first rank. So the 2 of hearts should have been at the very top of the deck, and the first one created. Let's confirm that with the very last value. The very last thing at the bottom of the deck, so to speak, should be clubs, and then if we go all the way here, should be ace. So that means if I were to scroll down here, and instead grab the very last card by saying -1, go to the very end of the list. So we'll call this the bottom card. And it's up to you whether you want to think of the beginning of the list as the top or bottom of the deck. So there's the bottom card, we'll say. And now if I print the bottom card, I get back the ace of clubs. So this is actually working. And now I could say for card object in new deck all cards, go ahead and print that card object. And I see 2 of hearts, 3 of hearts, and so on. So what this is doing is all cards holds various card objects. And then recall card objects, when you print them, return back their rank of their suit. Perfect. So what else do we need to add to this? Well, right now, if I create a deck, it's always going to be in order. It would be nice to be able to shuffle a deck through a nice method call. So now let's create that. And make sure you pay very close attention to the indentation here because we're actually several levels deep. We want to make sure this new method is aligned with all the other method calls. So we will call this the shuffle method or shuffle deck method, whatever you want to call it. We'll say self here. And then what we need to do is we have this internal list of card objects. And it should already exist because upon instantiation, it magically, well, not really magically, but it just creates it for us. And what I need to do is now shuffle that list. And I know that if I have a list, for example, if I have the list 1, 2, 3, 4, 5, and I want to shuffle it, I can say from the random library, random.shuffle my list. And now if I take a look at my list, it's been shuffled. So a couple of things to note here is that in this case, I'm calling random.shuffle. The other way to do this is to say something like from random import shuffle, and then if you wanted to, you could just call shuffle like that. But in our case, since we only imported random, I will call random.shuffle. So that's the way the imports work here. And you can check out the modules and package series of lectures to further understand this. But the thing you need to know right now is that what I'm doing is I'm calling the shuffle function from Python's built-in random library. And we know that it shuffles a list. Okay, so what's important to note here though is random.shuffle actually does not return anything. It does all of this in place. That is to say that I can't actually assign the result of the call random.shuffle. So if I have my list, and I were to try to do this, shuffled list is equal to random.shuffle, what's going to happen is my list will still be shuffled. However, the shuffled list is nothing. It doesn't actually exist. So if I check type, it returns nothing. So that is to say random.shuffle does not return anything when you call the function. Instead, it just does everything in place to your original list. So if we come back up here and start thinking about our shuffle method for the deck, what do we actually want to achieve here? All we need to do is internally shuffle all the cards. So what I should be doing is call random.shuffle on self.allCards. Now, do I need to return this? In this case, no, because recall, random.shuffle does not return anything, and I don't actually really care about storing the result anywhere. Instead, I want to know that the particular instance of the deck I've created has been shuffled. So what we're going to do here is I'm going to rerun this cell to make sure that new method call is in there. And then what we're going to do here is create a new deck. And let me delete these 3 cells that we created. And let's go ahead and grab that bottom card. So what is my bottom card right now? It's Ace of Clubs. However, let's now take that new deck and call the shuffle method on it. That's shuffle dot shuffle. And now let's take new deck. In fact, let's just print new deck all cards. Let me just copy and paste that here. And note now it's the Jack of Hearts, which means internally this dot all cards list has been shuffled and everything's now in a different order, which is exactly what we want to achieve. So this happens all internally with the built-in all cards attribute, and nothing's actually being returned to you when you call shuffle. Instead, it's all happening within that deck class. More specifically, it's all happening to the all cards attribute, which is just a list of card objects, which is why I'm able to print it, or at least print one of them here, the very bottom one. And if we take a look at the very first one, it's no longer the 2 of hearts, it's a 7 of diamonds because it's all been shuffled. Now the last thing to note here is currently all cards will always have those 52 cards. I've been able to create those unique 52 cards, and I've been able to shuffle them around. In a real game though, when I have that deck of cards, I need to be able to remove actual cards. And let's go ahead and create a method that can deal 1 card, essentially grabbing one of the cards from somewhere in the list. So I will say def deal 1 takes in self, no parameters necessary here. And what I want to do is I want to return a single card. So I will say return self.allCards. And because all cards is a list, what I can simply do is call the pop method off of this. So let's think about what this is doing. I have this attribute all cards, which is a list of these card objects. If I want to remove one of these card objects and return it in order to use it for whatever other classes need it, then I will call deal 1, and it will take that list of all cards and then pop one off and essentially return it to me. So let's rerun this and make sure that works. So I will run deck again to make sure it has the deal 1. And then let's create some new cells here. I'll redefine new deck. Let's go ahead and shuffle the new deck. And now I'm going to say my card is equal to new deck. And I will say deal 1. And now notice my card should be a card object somewhere in memory. And there it is. I have this card object somewhere in memory, And if I print this out, it'll report back to me what card I actually have. So I got the 6 of spades from this deal. However, the important part to note is let's check the length of new deck, all cards. And notice now it's 51 cards. When a standard deck, it's 52 cards. So what happened here? I have now essentially permanently affected the current cards within the deck. Because I removed one with .pop, all cards now only has 51. And eventually what's going to happen is if you deal them all out, then you may get an error on deal 1 by saying there's no more items in this all cards list to pop off. Okay, so again, what we did here is we created a class deck, and then what we're going to do is upon instantiating it, you essentially refill all those 52 cards that are unique. You have the ability to now shuffle the deck, and you have the ability to remove a single card from the deck. And because you can remove a single card, what I could do is simply run a for loop and say deal 1 52 times if I wanted to remove all the cards from the deck. So actually just being able to deal 1 card is enough for our use cases. If you want, you could expand on this to deal 2 cards at a time, 3 cards at a time, or so on, or split the deck in half, etc. But really, with just the deal 1 method, we have enough that we can use outside Python logic in order to call deal 1 method as many times as necessary. Okay, so that's the deck class. Coming up next, what we're going to do is create a player class. And the player could then actually hold cards in what it will call their hand. So what we're going to do is explore that in the next lecture. I'll see you there. Welcome everyone to this lecture on the player class. The player class will be used to hold a player's current list of cards. A player should be able to add or remove cards from their hand, that is, their list of card objects. And we're going to want the player to be able to either add a single card or multiple cards to their list. And we're going to explore how to do this in a single method call. The last thing we need to think about is translating a deck or hand of cards that has a top and bottom to a Python list. Now we're going to try to visualize this to explain it, but the basic premise is if you have a real physical deck of cards in your hand, then you have a top and bottom. And when you want to draw a card, you typically draw from the top. And if you're going to add cards that you won in the game of war, you're going to put them at the bottom of the deck. Now a Python list goes from left to right. So essentially what we're going to do is translate top and bottom to left and right using a Python list and using indexing, where we know 0 is towards the left and -1 is all the way towards the right or the very last item. So let's visualize this. The player class will have a self.allCards list, very similar to what we saw in the deck class. And for simplicity here, I'm just going to create a list called cards, A, B, and C. And let's explore the different methods of adding and removing cards. So I have 3 cards here, A, B, and C. A is at index 0, and C is at index 2, or really index -1, where -1 is the very last item in a list, regardless of how long it is. So for A, B, and C, let's say a player is going to play a single card. We want to play it from the top of their hand. So that means when the player plays a single card, we're going to use pop. However, we'll specify that pop is at 0, which is the very first item in the list that we want to pop. So that means we're left with cards is equal to B and C. So when a player plays a single card, which is the way we're going to do this, they're going to pop at 0. Now let's say a player is going to add a single card. We want to add this card to the bottom of a list. Now lucky for us, if we're going to add something to the bottom of this deck or the end of a list, then that's simply just using the append method, because by default, append is going to go to the end of a list. So I'll simply say append, and in this case, this card is called W. And now my cards in my hand is B, C, W. Now let's imagine that we went back to my hand being BC. However, now I need to add in multiple cards because let's say I won a very large round of war and now there's multiple cards on the table that I now have to add in back to my hand. So I have cards is B and C and new is X and Z. So what I will do here is I will use the extend method because the extend method allows me to now have a list B, C, X, Z, and where all of those are going to be a single item. So extend takes a list and then essentially merges it with the existing list. So this is cards.extendNew, where if we looked back, new was X and Z. Now this sometimes often confuses students because they were thinking of just using append again. However, we cannot use append. Why not? Because if we were to append a list, suddenly I'm getting a nested list. And that's going to mess stuff up when I start trying to draw cards again, because I'll end up drawing a list instead of a single card. So do not use append in this case, because you're going to have some nested lists, which is going to ruin the logic later on of removing cards from your hand. So that's why we're going to use extend. Okay, let's get started and head to a Jupyter Notebook and actually code this out. All right, here we are in the notebook where we left off last time, and let's begin creating our player class. First things first, we need our instantiation method underscore underscore init underscore underscore. And this is going to take self, and then we have to think, what should a brand new created player have? Well, in order to distinguish one player from another, let's go ahead and have each player have a name. So we'll say self.name is equal to name. Each new player should also have what is essentially an empty hand. So I'll create an attribute called allCards, similar to the attribute in the deck class, and it's going to start off as an empty list. And then what we want a player to be able to do is remove cards and add cards to this allCards list, what is essentially their current hand of cards. So again, make sure we check our our indentation here. And then we'll say remove one, and right now I'll just have pass there. And then I'll create a method for also adding cards, has self, and then it should probably take whatever new cards are going to be added. And then we'll have a pass there just as filler for right now. And let's go ahead and create a string method. That way we can print out a player. And it's really up to you what you want to return for the print statement. But in this case, let's go ahead and I'm going to use an f-string literal here to essentially fill out information. I will say player and then call self.name. So essentially it's going to grab that player's name. So we'll say player self.name has, and let's go ahead and report how many cards they have. So that should be the length of self.allCards, and then outside of this bracket, I'll say cards. So let's first check that our instantiation method works, and then we can print out a player. So we run this. Let's create a new player. So this new player will be an instance of a player object, and we'll give him the name Jose. And then let's go ahead and print out this new player. Tab autocomplete there. Run this, and it says player Jose has 0 cards. Okay, looks like everything's working so far. So now we have to decide, how do we remove a card from this list of cards? Well, in this case, we can simply do just like we did before. We will say return self.allCards and say pop. Now remember, what I need to do here is specify pop at 0, because when I remove one card from the list, like we previously discussed at the beginning of this lecture, I want to make sure it happens from the top or from the beginning of the list. Now it's time to figure out how to add cards. New cards, we're going to say new cards can either be a single card object or a list of card objects. So we'll do an if statement here. We'll say if this is a list, so if the type of new cards is equal to the type of an empty list, which is a list, then we have multiple cards that we're adding. So I will say self.allCards dot extend that list of new cards. Now, if we don't have a list of cards, then we have a single card. So we'll say else self.allCards append new cards. So what this is doing is this first one, this is for a list of multiple card objects. And this second one is for a single card object. Okay, so we're able to now remove a single card, and now we're able to add multiple cards at once or just add in a single card. So we'll go ahead and run this. Let's go ahead and create that new player. New player still has 0 cards, so let's go ahead and add a card to them. We'll say new player, add cards, and now what we're going to do is if we take a look up here, recall that we have this my card object. Let's make sure it's actually working. So we'll say my card, whoops, looks like it's not defined, and has no space or underscore there. There we go. Okay, so we have this card object, and if we print it out, it's the 6 of spades. So what I will do here is in this call, new player.add cards, I'm going to add my card. And now, if I take a look at new player, I have this player object, and if I print the new player, it says player Jose now has 1 card. And so what I could do then is say new player, all cards at index 0, print it out, and you'll notice I should get the 6 of spades. Perfect. Now let's go ahead and add multiple 6 of spades. Just to make sure it's working here, we're going to say new player, add cards, and I'm going to create a list here of my card, my card, my card, essentially grabbing that separate card object that we made, which was a 6 of spades, and I'm going to add it multiple times. We won't really be doing this in the game logic because there's only one instance of each unique card, but in this case, essentially we're imagining that I'm duplicating that 6 of spades outside, and then I keep adding it to my hand. Okay, so now I should have 4 cards. That original 6 of spades that I added, and then these 3 more. And what's nice is I can add this as a single card object or as a list of card object, due to the fact that I'm checking here if it's a list to extend or if it's a single one to append. Which means if I print out my new player right now, it says player Jose has 4 cards. Perfect. Let's make sure that our removal method works. We'll say new player, remove 1, open and close parentheses, run that. It basically returns back that card object. And now let's print the new player again, and they should only have 3 cards now. And there it is. All right, so it looks like our player class is working. We can add a single card, we can add multiple cards, and we can clearly remove a single card. Later on, due to the way we write the game logic, we'll see that we don't actually need to remove multiple cards. Instead, we'll just use a for loop to remove as many cards as necessary. Coming up next, we'll begin working on the actual logic of the game. I'll see you there. Welcome everyone. To finish off this war card game project, we have to actually continue with the game logic. So this is part 1, where we're going to be visualizing the logic, and in parts 2 and 3, we'll actually code it out. So keep in mind that creating the overall logic is actually often the hardest part of a project like this. It's also really important to note that in general, we plan the classes around the upcoming logic. So in a real-world situation, you're often thinking of both the logic that your application, or in this case a simple game, will have, along with the class structures at the same time. And the reason for that is, you'll notice that as we actually go throughout this game logic, the classes we've created fit perfectly. And that's because we designed the logic along with the classes when creating this notebook and project for you. In general, in the real world, you wouldn't just randomly create classes and then hope they kind of fit into your logic. You're actually going to be thinking about both of them at the same time. As you sketch out your logic, you'll realize what classes are necessary, and then you'll start to construct those as well. So keep that in mind. In a real-world situation, you're typically working on both the logic and the class structures more or less simultaneously in order to make sure that they're a good fit for each other. And a last note is at the end of this actual warm-up project notebook, you'll notice there's a bunch of links to other different implementations of the war card game you can check out. For instance, some of those implementations, instead of having, or in addition to, a player class, they have a table class, where the table class represents what cards are actually currently on the table. So that may be something you may want to explore as well. But for our case, our classes should be enough to play the simple game. Okay, so let's outline our logic for the game. We're going to do this visually. So the first thing we have to do is create 2 instances of the player class, player 1 and player 2. And essentially these will both be computers. And then we're going to create an instance of a new deck. And recall, a new deck has everything perfectly in order, So when we actually split the deck between the players, we want to make sure that we call the shuffle method first. Once the deck has been shuffled and it's in random order, then we can split it between player 1 and player 2. There's lots of different ways we could do this. In our case, we'll just use a simple for loop to kind of stack half the deck to player 1 and half the deck to player 2. So now that the players each have half the deck, it's time to actually go through the game. To know whether we have to go through the game logic or not, we should probably check to see if somebody has already lost. At the beginning, we know this won't be the case, but we can have this check anyways, since we're going to be calling it after each round. So here we're going to check throughout that Python list. Remember, each player has a Python list of the cards. And we essentially check, do they still have cards left? Is the length of this list equal to 0? If it's not, then we can have some Boolean value called gameOn equal to true, and we know the game can continue playing. So obviously at the first round, both players still have cards, so we continue with the game. And so now we're going to have kind of this outer while loop called gameOn or while gameOn, and we can either say gameOn is equal to false, or we can even call break to break out of this while loop once a player has lost. But in this case, both players still have cards, so the game still goes. So what happens now? Each player draws a card or removes a card, and then we do a comparison against those cards. Depending on who won that comparison, in this case, we'll assume it's not a tie, then that player wins both those cards, and we add both those cards. Technically, those cards should go to the bottom of that stack, as we previously discussed. However, recall there's the case for war. Essentially, what happens when both players draw a card, and those cards happen to be equal to each other. In this case, we have that instance of war, which means the players need to draw additional cards. This can vary depending on what game rules you use. What we're going to do is we're going to draw an additional 3 cards. So we're also going to have a while at war loop within the while gameOn. Now you may be thinking, why do I have to do a while loop for at war? And the reason for that is because sometimes you could get 2 wars in a row. You can have 2 cards that are equal to each other, draw the extra cards, and then upon drawing that new card for the new matchup, you may get another tie. So in which case, it's easier to program this out thinking of while at war, where at war is conditioned on whether or not the current matchup has the cards equal to each other. So that way you don't need to worry about having to deal with multiple ties in a row. So we just say, while at war, you're going to keep drawing those extra cards and then do the comparison. So we can do this comparison then over and over again if we have multiple ties in a row. So let's say in this case, the tie is ended and one of these players has won. We'll go ahead and just say player 2 has won. So now they get all those cards added to their hand. And then before we continue with that while gameOn loop, we're going to check, has a player lost? In this case, looks like player 1 has 0 cards. So then we can say something like gameOn is equal to false. Or alternatively, you could just use break to break out of that upper while loop. And in this case, then we announce player 2 has won. Okay, so that's the logic for the game. What we're going to do in the next series of lectures is actually program it out. I'll see you there. Welcome back, everyone. In the previous lecture, we visualized and discussed our game logic. Now it's time to actually program it. Let's head back to the Jupyter Notebook. Okay, here I am at the notebook that we've been working with. So in this notebook, there's a couple important things. I have my player class defined, my deck class defined, and then my card class defined, as well as suits, ranks, and values, and this import random call. So that's already all defined and has been run in this notebook. And basically, there's going to be just 3 major parts to this. One is the game setup, actually creating the players. So we'll do that kind of all in one cell. And then the next part is going to be essentially the while loops. And there's 2 of them. It's gameOn, the main logic, and then we'll have to check in an indented while loop, so while the game is on, in case we are at war, so to speak. Okay, so let's start with the game setup. This is the easiest one. We create those 2 players. We will say player 1 is equal to an instance of the player class, and let's just give this person the name 1. So it's easy to identify. And then we'll say player 2 is equal to, we will say player 2. And then we have to create a new deck. So we'll say new deck is equal to an instance of deck, and let's shuffle that deck by calling the shuffle method on it. Recall, nothing's returned here, it just shuffles the list inside of deck. And then, after we're done shuffling it, we have to split this deck between both players. Lots of different ways you can do this. One simple way is to simply say, for X in range, 26. Why 26? Because a deck has 52 cards. Half of 52 is 26. And the reason we use half here is because we'll say player 1, and we're going to say add cards. And we'll say from that new deck, go ahead and deal 1 card, open and close parentheses, since that's a method call. And we will do the exact same thing for player 2. So what's happening here is basically 2 cards at a time. We add 1 to player 1 and then 1 to player 2, which is why I don't go through all 52. I just go through this 26 times. So I'm adding 2 cards for each iteration in this for loop. So I run that. Looks like it worked. And one quick way to confirm this is if I say player 1, all cards, and just check the length of that, then I can see they have 26 cards. And I can then also, for instance, print out their very first card, and I see they have here the King of Hearts as their first card. All right, so finally, we'll say the game on is equal to true in order to make sure that we actually start off this while loop correctly. So we have this while game on loop. So what are we going to do here? We'll say while game on. And outside of this, let's go ahead and have a counter called round number. And we'll set it at 0. And then for each round, I will say the round number is plus equal to 1, essentially adding 1 to my current counter. That way I can print this out and see how many rounds it's taking to actually play these matches. So we'll say currently on round, and then round underscore num, using f-string literal to basically print round number. So this is round, and then we'll start off at 1, then 2, then 3, then 4, then so on. Okay, so we're printing out the rounds. What do we have to do first? We should probably check to see if a player is out of cards. We know that won't happen on the very first round, but it may happen later on. So we'll just keep doing the check at the top of this game on. So we'll say if the length of player 1, all cards, is equal to 0, that means they have no cards left. So in this case, player 1 has lost. So we say player 1 out of cards. And we can then say also as well, player 2 wins. And once we're done with that, we'll go ahead and say that game on is now equal to false. And to just not even bother continuing over everything, we can break out of this while loop, which is essentially going to happen anyways because game on is equal to false here. We'll say break, and that essentially ends the game there. Now we need to do this as well for player 2. So I'm just going to copy this and paste it here, except instead of player 1, I'll say player 2, all cards, and then say player 2 loses, and player 1 wins. So if the length of player 1's cards is equal to 0, then they're out of cards and player 2 wins. Game on is equal to false. Break out of this whole loop, break out of all logic that's happening here, and the game's over, round number, whatever. Then player 2, if their cards are equal to 0, or the length of their cards is equal to 0, they're out of cards, player 1 wins, same thing. Otherwise, the game is still on. So what I will do here, in order for the game to continue, is it's time to start a new round. And the new round, we're going to say player 1 cards. And this variable, you can think about it as the cards that the player is going to leave on the table. So it's going to be an empty list. Something I want to make clear here is that player 1 all cards is not going to be the same thing as player 1 cards. You can think of player 1 cards as the current cards in play versus all cards, which is the cards that that player has essentially close to them, face over on their hand, or face down, I should say. Okay, so player 1 cards, and then we'll also say player 2 cards. and these start off as empty lists. If we're going to start a new round, then all we need to do is remove a card from their list of all cards and append it to the cards currently in play. So we will say player 1 cards, and I'm going to append, in this case, player 1, remove 1. And then we'll say here the exact same thing we have, so I'll just copy and paste this and switch this to 2 cards, or player 2 cards. Okay, and then we'll have to start checking the actual comparisons, which will be in the next lecture. But let's just do a quick overview of what we did here. We set up the game, player 1 and player 2 are ready to go. We created a new deck, we shuffled it. We split the deck between the players. Tons of different ways you could do this. Then we set a variable just to have the game continue kind of until someone loses. We print out the round numbers, check to see if anyone's losing. If they have lost, then they'll go ahead and just X that out of the while loop. If not, it's time to start a new round. Player 1 cards, it starts off empty. We grab a single card, remove it. Player 2 cards starts off empty, grab a single card and remove it. Next, what we're going to have to do during this kind of while at war is start checking to see if the cards are greater than each other, less than each other, or if they happen to be equal, then we will use an actual war comparison in order to keep appending more cards. Okay, so what we'll do is continue with this in the next lecture. I'll see you there. Welcome back, everyone, to part 3 of this game logic series. So now it's time to check the players' cards against each other. And I want to point out and make it clear that there's tons of different ways this can be done. Definitely do not take the while loop method we show here as the only way to do this. And as I previously mentioned, at the bottom of the notebook, there's lots of other implementations of the war card game in Python that you can check out just to explore other ways of thinking about it. But as we continue, in general, regardless of how you actually program this, there's really only 3 possible situations when the players first compare that first card. And that is either player 1 has a card greater than player 2's, player 1 has a card that's less than player 2's, essentially saying player 2 is greater than player 1, or, in the case of war, their cards have equal value. The way we're going to write this is with an if, elif, else within a while loop. And that assumes that a war has happened, which is a little strange at first, but hopefully once you see the logic, it actually makes a lot of sense to you. So what we're going to do is we're going to state that at war is only equal to false if the players resolve the matchup on that first drawn card in those first 2 situations. We'll just say, hey, at war is equal to false. No need to worry about this at war loop. We'll just break out of it. So we start off assuming at war is true, and we break out of at war while loop by saying it's false if the players resolve their matchup. Otherwise, we won't say anything and at war will remain true, and then we add cards to the current cards on the table, drawing those extra cards for the actual war. As a quick note, we're going to be playing with some special rules, and that is the rules in this version is that each player needs to draw 5 additional cards if there is a tie. So that is to say, when a war does occur, we'll go ahead and add another 5 cards from the deck. A lot of times people use 3, but the reason we're going to up it to 5 is just to make sure the games don't last too long. The lower that number is, the longer the games are going to last, and sometimes they can last thousands and thousands of turns. So the higher the number, the higher or the faster the simulation will go. And the other point we're going to make is that the player will lose if they don't have at least 5 cards to play in that war. So obviously, this logic can be easily edited, so you can change that number 5 to really any number you want. You can change it to 3 or so on. And you can also say that maybe the player has to use all their cards at the end if they have less than 5. But we'll go ahead and say if they don't have at least 5, or at least some specific number, they go ahead and lose. And all of this is just to avoid having to run the simulation for thousands of occurrences. And if you check out the lecture notebook, at the very end, I've linked some interesting statistics of this war card game. So here's a simulation of the number of occurrences versus the number of turns to win. So essentially, how many times do the cards actually match up and get flipped? How many rounds occur? And it's also different whether you shuffle the cards or you don't shuffle the cards. And in some instances, if you don't shuffle each player's cards before each round, they sometimes get perfectly stacked in a loop where you kind of have this infinite loop where war will never occur because each player's cards of 26 cards each are perfectly stacked, so it's one time one player has beaten player 2, and then the next time player 2 has beaten player 1, and so on and so on. And you get kind of stuck in this weird infinite loop. In fact, this chart right here actually artificially is cut off at 5,000. And you can check out the lecture notebook for the link to this full blog post. Okay, so we're going to quickly explore this loop visually before we code it out, just to make sure it's clear to everyone. So the actual comparison game logic, this is happening within this while loop of while at war. That's within the while game on loop. So we start off outside of this loop by saying, hey, we're going to assume that war is true. So while at war, we'll start the comparisons. The first comparison is going to check if 1 is greater than 2. If that happens to be true, then we will add the cards currently present on the so-called table, those 2 cards. We'll add those cards to 1 or player 1's hand, and then we'll say at war is equal to false, so we break out of this entire loop. Elif, so the other situation we're checking for, is if 1, the value of player 1's card, is less than the value of player 2 card. If that's the case, then we add the cards to player 2, and then we say, hey, there was no war here, at war is equal to false. However, for the else case, we haven't set at war equal to false yet, so we assume that at war is true. So now we're going to do the following. We're going to check if the players have enough cards. As I mentioned, the rules we're using here is if you don't have at least 3 cards to draw the war, so you'll lose the game. So if the players have enough to actually commit to that war, then we draw those additional cards. Once you draw those additional cards, and this is why we use this while loop, we'll say, hey, start back at the top, and now check that top card that has been newly drawn with these if statements again. So what's nice about using this kind of at war starts off as true, and then we continue while at war, is this accounts for the fact that you may have multiple wars in a row. So because of this, if we happen to then again fail that if elif check, we come back to the else, draw the additional cards again, and then keep going over and over again until this series of wars, or single war, has been resolved. Once that's true, we'll start back up the top with the while game on, and draw the single card, and start this all over again. Okay, so let's see how this is actually programmed out in Jupyter. Here I am back at the Jupyter notebook we were working with last time. Recall we have our while game on portion of the while loop. We check to see that the players still have cards to play. If they do, we start off a new round, grabbing 1 card each. And now it's time for this while at war loop. So as I mentioned, we're going to assume that the war is happening, and then we'll look for cases to end it. So say while you're at war, and note the indentation here is extremely important. So if you're getting an error, it's very likely you have an indentation error or you made a simple typo, especially when we're calling things like player 2 all cards versus player 1 cards. If that happens to be the case, go ahead and copy and paste from our lecture notebook. Okay, so while you're at war, we'll start doing that if check. We'll say if player 1 cards, and what I'm going to do here is say -1 dot value is greater than player 2 cards -1 dot value. So in this case, player 1 has beaten player 2. Now you're probably wondering, why are you using -1 here? Well, that's because on the assumption that we get to war, player 1 cards is eventually going to be a stack of cards. And what I want to make sure is that by choosing -1, I'm not going to be constantly choosing the very first card that was played. And that will be more clear since we're going to be appending cards to the end. So just to show you a quick visual example, let's imagine that player 1 drew a queen, and let's imagine eventually it goes down to war. So next they add some more cards there. Let's say they add Jack and King, and then their final card they're going to draw will be a new one, so that might be a 4. So what happens is, by calling -1, if we happen to go to war, I am going to draw this new card. If I didn't have -1, if I had 0 there, then if I append these towards the end, what's going to happen is I'm going to constantly be comparing against that first card, which will accidentally make this kind of go on forever, because the players will constantly be drawing the very top card that they had originally drawn. So the reason I use -1 here is because it will always draw that last card. And conveniently, if you only have one card in that list, it's just going to draw that card. So that's why we're using -1 there. So if player 1 cards, -1, in this case at the very beginning is just one card, if that's greater than player 2 cards, -1 value, then player 1 gets the cards. So we say player 1, add cards, and we'll say player 1 cards, and then we'll say player 1, add cards, add player 2 cards. Now what's really nice about the way we set this up, and that's why I mentioned the logic you're often thinking about the classes as well, is that add cards works for both a singular card as well as multiple cards. So what's nice about this is I can now say player cards is just a single card object or a list of card objects. So player 1 gets all their cards back, and they're also adding the addition of player 2 cards. And now we're no longer at war, so we will say at war is equal to false, which breaks us out of this comparison loop for at war. We come back up here, and then we'll continue by checking, hey, is someone lost yet? If not, start the next round, and then we continue here. So it's up to you if you want to call this at war. You could also call this something like comparison still going, which might be a more appropriate variable name, but just want to make it clear to you here. Now, we also have the check to see if player 2 has won. So this is so similar that I can just essentially copy and paste this code actually. So I'm going to do that. I'm going to copy and paste this, and wherever 1 or player 1 is, switch that to player 2, and wherever player 2 is, switch that to player 1. So what I'm going to do here is say elif player 1 cards is less than player 2 cards, then player 2 has won. So player 2 will be the one adding those cards. So just 3 changes we have to make here. Check the comparison the other way. So now player 1 is less than player 2, so we will add the cards to player 2, both player 1 cards and player 2 cards. Finally comes the else statement. So if the card is not greater than or less than, then by default they have to be equal to each other. And this is where we have a war. And to visualize this a little bit, I will say war. That way, as this game is running, we can see how many times war pops up. So essentially, we should be seeing something like round 1, round 2, round 3, and then all of a sudden we'll see something like war pop up. Okay, so I previously described that you're going to lose the game if you don't have enough cards to actually play a war. So up to you if you want to add in this logic or not, but we'll say if player 1 all cards is less than 3, essentially they can't play a war, we print something like player 1 unable to declare war or play war, however you want to phrase it. And then let's go ahead and print one more line saying player 2 wins. Okay, and now what we're going to say here is because the game is over at this instant, we can say game on is now equal to false, and I'm just going to break out of this while at war. So break here is going to break out of this while at war, and game on being false will end this overall while loop. And I'm going to do the same thing now for player 2. So we'll say elif length of player 2, all cards is less than 3. Go ahead and say game on is equal to false. Player 2 has now lost, so we'll say player 1 wins, and player 2 unable to declare war, break out of this. Else, what are we going to do? Well, in this case, we simply just have to add more cards. So up to you how many cards you want to add in here. We'll say for num in range 3, we'll say they have to add on 3 cards. Then player 1 cards, append, player 1, remove 1, and then we'll do the exact same thing, so just copy and paste this, for player 2. So that each essentially calling remove 1 3 times. Okay, there we have it. And this is the total game logic. So before we actually run this and check for typos, let's do a quick overview. I'm going to zoom out a little bit so we can see the whole thing. Create the 2 players, create the deck, shuffle it, split the deck between the 2 players, the game on, so game automatically starts off as on. We have this round number counter right off the top. While the game is occurring, we have to continually check, Are the players still eligible to play? Has one of them run out of cards? If not, we start a new round, so that removes one card, and then we have this comparison check. So we'll kind of assume that war could happen. If player 1's greater than player 2, war doesn't happen, we set it to false. Player 1 gets both those cards. Else if player 1 is less than player 2, then player 2 gets both those cards, war's over. Otherwise, war has happened, and within a war, really the comparison is not occurring. All that's happening is, or the final goal is to just add those cards. So quickly, depending on the way you want to write these rules, you have these checks here to say, hey, they're unable to play war, so you could have a loss here. Otherwise, you can make a check here to just say, okay, get the remaining cards. So maybe if they have 2 or 1 cards left, you could write this to just say, grab all remaining cards of player 1 or player 2. And then we'll go ahead and add those cards here, and we append them, which is part of the reason of why we use -1 up here, because they're going, at least the new cards are going towards the end. Okay, so before we run this, at the beginning of this lecture, I did mention that the higher this value is for how many cards you have to draw during war, the shorter the game is going to be. So let's go ahead and just change this to 5. That way they draw more cards upon war, and there's a higher likelihood for them to lose sooner. Okay, so I just changed these to 5. Again, these are numbers you can edit, and this is essentially where you can kind of change the code to change the rules of the game. And you can check out the Wikipedia article that I also linked to at the bottom of the lecture notebook to essentially explore different gameplay rules. But let's go ahead and run this and make sure it all works. Okay, so we went for about 223 rounds. There was a war at the very end, and then at the very end, player 2 was unable to play war, so game over at war, and player 1 wins. And if we scroll back up here, it looks like we had 2 wars in a row right there. So it looks like our while loop was working, and that's quite a bit of rounds there. So let's run it one more time. Let's take a quick note of who won the last one. So player 1 won last time. So to run this again, I have to reset the players. Game on is true, and let's run that cell again. Okay, so 104 rounds, player 1 wins again, and let's run this just a few more times to make sure there's no mistakes. That way, we'd like to see player 2 win a match eventually. So we scroll all the way down. Player 1 is out of cards, and player 2 wins. Perfect. So always good to check that both players have the capability of winning here. And it looks like our code is working. Definitely check out the lecture notebook. There's a bunch of links at the bottom of it just discussing the game of war, how to program it, the statistics behind it, the rules behind it, and so on. But overall, what you should have understood is how to use object-oriented programming to create a simple application. The main things being here are the classes we created at the beginning, and then the fact that the, for instance, deck class could use instances of the card class, and that the player class could hold instances of the card class as well within its card list. And the fact that then you can connect everything through some logic. Okay, thanks, and I'll see you at the next lecture where we will begin discussing your second milestone project. Welcome back, everyone, to your second milestone project. So we've now learned enough about Python with object-oriented programming, errors and exception handling, as well as functions, enough to actually start a larger set project. And in this case, it's going to be our second milestone project where we're going to be creating a blackjack game with Python. Now you can approach this project one of a few different ways. First off, if you're still feeling a little bit fuzzy on object-oriented programming, or you need more of a helping hand as you go along for your first large project, what you can do is just code along this project with the solutions lecture. A lot of students really like that approach, especially if they still feel a little bit too new to object-oriented programming. They'll jump straight to the solutions video and then code along with that actual video, and it's a nice way for someone to help guide you on creating a larger project. The second approach is almost the complete opposite, which is just to attempt the project on your own. So we actually suggest that students who feel very confident in object-oriented programming or who just like that extra challenge to, after viewing this lecture, just jump straight to a blank notebook or a blank script and get started. Debug, test things out, and play around with Python to see if you can build the game completely on your own. Then we kind of have an in-between, which is the workbook. So just like the first milestone project, we actually have a full workbook which breaks down the entire project into smaller, more handleable sub-problems for you to basically help guide you along as you attempt this project. And then there's a solutions lecture that goes through that workbook as well. So again, feel free to take the approach that is best suited for you, depending on how you felt with the material that we just covered. So as I mentioned, for this project, you're going to be using object-oriented programming to create a blackjack game with Python. So I want to quickly go over the main idea of the game, discuss how object-oriented programming should be used for this project, and then give you a brief overview of the workbook notebook for this project. So for our version of the game, it's going to be a simplified version of blackjack, where we're only going to have a computer dealer and a human player. And we're going to start with a normal deck of cards, and you're going to create a representation of that deck with Python using object-oriented programming. So let's quickly just go over what our actual game will look like. This is for people who are unfamiliar with blackjack, or if you are familiar with blackjack, we're going to discuss things that we don't need to consider or we'll just ignore for our version of the game. So the very basic concept of the game we're going to implement with Python is that we have the computer dealer and then the human player at the keyboard and a deck of 52 cards. Then what happens is the human player, they have a bankroll, so you can hopefully already start thinking that they're going to have an attribute for their bankroll, just like we discussed when we talked about creating a bank account for our previous object-oriented programming challenge. And from that bankroll, the human player is going to place a bet, indicating whether or not they think they're going to win this set of hands. Then what happens is the player starts with 2 cards face up, and the dealer starts with 1 card face up and 1 card face down. The player goes first in the gameplay, and the player goal is to get closer to a total value of 21 than the dealer does. And the total value is just the sum of the current face-up cards that the human player has. And there's 2 possible actions that a human player can take. They can either hit, which is to receive another card from the deck, or they can stay to stop receiving cards. We're going to ignore actions like insurance, splits, or double downs, which happen in a real casino playing blackjack, but we want a simplified version of this game, so all the player has to be able to do is hit, which is to grab a card from the deck and put it in their hand, and then take a new sum there, or stay, which means stop receiving cards. So for example, they could hit, get a new card, and then they check what their sum is. And remember, they're trying to get closer to the value of 21 than the dealer will. So once the player has gone, their turn has ended, and then it's the computer's turn. If the player is still under 21, then the dealer hits until they either beat the player or the dealer busts. So by bust, we mean that you go over 21. So let's see possible ways that the game can end. First off, if the player keeps hitting before the computer even goes and they go over 21, then they bust and they lost their bet. The game is then over and the dealer collects the money. So that's one way that the game can end, which is the player busting. And this is before the computer dealer even has to go. The second way the game can end is if the computer beats the dealer. So what happens is the human player goes, they start collecting cards, and then they decide to eventually stay. So for example, their current sum is 19. Then the computer dealer goes and they start hitting cards, so they collect cards from the deck. And if they have a sum that's higher than the human players and is still under 21, then the computer has beat the dealer. And then finally, the third possible option that the way the game could end is that the player actually wins after the computer has its turn. So in our simplified version of the game, what's going to happen is the computer dealer keeps hitting until they either beat the human player or until they bust. So eventually what may happen is they keep hitting and then they bust, meaning they go have a sum over 21. And if that's the case, the human player wins and they actually then double their bet money and that goes to their bankroll. And we have a happy human player. So let's talk about a few special rules that you're going to have to implement. One is that face cards, such as the Jack, Queen, and King, are going to count as a value of 10. So we're going to be walking you through how to actually create a representation of a deck of cards, and those face cards are going to have a sum value of 10. And then here's the tricky one, is that aces can count as either a 1 or 11, whichever value is preferable to the player. So if you have an ace in your hand, you can either treat it as a 1 or an 11. You can check out the resource links for more explanations of blackjack and more information on that. But what we're going to do now is explore the project itself and the workbook. Let's get started by jumping over to that repository. Okay, so here we are at the repository. If you go to Complete Python 3 Bootcamp, you should see a folder that has the Milestone project. Keep in mind that the numbering might be a little different if we add folders in the future or rearrange things, but the name should be the same, Milestone Project 2. And what we see here are a few notebooks. We have the assignment notebook, and if you click on the assignment notebook, it basically just describes what the blackjack game is going to look like. We create a simple text-based blackjack game, players stand, hit, keep track of players' money. This is basically what I just described in those slides. And then the next couple notebooks is a walkthrough steps workbook. If we check that out, Here we see Walkthrough Steps Workbook. It's basically a kind of setup guide to how you should try to approach this project. And these are the basic steps you should follow when creating the game of Blackjack. And then if you keep scrolling down, we have cells with some essentially skeleton code here for you to fill in. So we can see we've created a class card for you. We have an empty init method, an empty string method for you to fill out. And then we have step 3, create a class deck, step 4. So this is to help guide you. And it's kind of an in-between between trying to do it all on your own at first or from trying to just jump straight and treat it as a code along project. Although that's totally fine. Either of those approaches is okay too. We try to give you as many options as possible for different learning styles. So this is a workbook just like you had for the first Milestone project where we slowly guide you through the various steps of creating this game. And at the very end, you're going to have what is essentially just a while loop here that goes through all the steps of the game. Then after that, the other two notebooks, one is the solution notebook that we're going to be going over in the next lecture, and then we also have a solution code notebook, and that's basically all the code that is in this workbook for the solutions in one cell. So in case you prefer using Sublime Text Editor or PyCharm or something that uses a .py script, you can use that solution code. That way you don't need to copy and paste from all the various cells in the workbook. Okay, so that's basically it. Again, you can kind of have 3 approaches here. Treat it as a code along lecture by just jumping straight to the solutions. And I would recommend doing that if you feel a little uneasy still with some of the object-oriented programming topics. This is pretty much the largest piece of code you're going to be writing so far. So a lot of students tend to prefer that code along project. The other way you can do it is by going through the workbook itself, the one we just described here, seeing how far you can get, referencing the solutions when you need to. And then the third way for more experienced programmers, maybe people coming in from another language, or people who just want that extra challenge, open up a fresh notebook and just get started and see how far you can go. Again, we're always here to help out in the Q&A forums. If you have any questions, you can feel free to ask there. We'll see you at the next lecture where we begin going over the solutions. Welcome back, everyone. In this lecture, we're going to start going through the Walkthrough Steps Workbook solution. I want you to keep in mind this is just an example solution. There's basically an unlimited number of ways you could have gone through this project, but in this case, we're going to go through the steps in the workbook. Let's get started. Okay, so here we are at the workbook. Lots of different things to get started with on the gameplay aspect. What we're going to do in this lecture is just go through these various steps and then fill out all the cells and see if we can create some logic at the end to actually get the game running. So here we see the game, and we want to set some imports and global variables. So global variables, those are variables we're going to be able to reference in other functions and objects. So we first wanted to import the random module. That was actually already done for us, and that's going to allow us to shuffle the deck prior to dealing. And you can check out the useful operators lecture if you want to review about how to shuffle from the random library. But what we want to do now is declare a couple of variables to store the card suits, the ranks, and the values. And you can develop your own system, but we actually have a lot of the code here for you. Where suits, we're going to set it as a tuple. So I'm going to copy and paste this here. And then the ranks, we have 2, 3, 4, 5, 6, all the way through Jack, Queen, King, Ace. So we can set that up as well. Again, you didn't have to do it this way. This is just so to follow our system along with the workbook. And then probably the most important part was this values. And this values is a nice dictionary where you can pass in the rank of a card and then get out its actual numerical value. This is really useful to us because when we're dealing with cards like Jack, Queen, King, we're not going to be able to directly read off the number itself, such as 2, 3, 4. So what we can do is just use this dictionary as a lookup so we can enter Jack into the values dictionary and get back 10. We'll set Ace right now to 11, but later on we'll deal with that special factor where it can be either a 1 or 11. So we're going to copy this and also paste this here. And then finally, we're going to declare a Boolean value to be used for controlling the while loop. Just like we did in that tic-tac-toe project, it might be nice to have a while loop that's dependent on some variable, such as game on. And in this case, we'll set it as playing is equal to true. So later on at the end, we can set playing equal to false if the game is over. I'm going to run that cell and move on to the class definitions. So what we wanted to do now was create a card class. And the card object actually really only needs 2 attributes the way we're going to set it up here. It just needs a suit and a rank. And then we want to have a string method on it so that when we actually print a single card, we get back something in the form of 2 of hearts or 3 of clubs. So let's set this up. Here we can see the init method, and we're going to add in 2 attributes, suit and rank. And then we'll assign those. Self.suit is equal to suit, self.rank is equal to rank. And then for the string representation, again, you have a lot of flexibility here, but we're just going to return something like self.rank concatenated with of, notice my spacing there, concatenated with self.suit. So we run that, and now we have a basic card class. And I want to note that it's okay if you either have open close parentheses here or no open close parentheses. It's only when you're using inheritance that you really need them. I usually prefer having the parentheses there. The notebook itself doesn't have them. It's really up to you which styling you prefer. And now we move on to step 3. So for step 3, this is where we wanted to actually store the 52 card objects into some sort of list that we could later shuffle around. And there's already a lot of code that's built out for you here. So we can see what the code is doing. We set self.deck as an empty list. And what's important here to note is even though this deck object has this attribute, self.deck, you can call it really whatever you want, it's not taking it in as a parameter when you actually first initialize an instance of the deck. And that's because when you initialize a deck of cards, you want it to be the same every time. You don't want the user to be able to input a parameter that would make something different with the deck. Instead, a deck should just be a standardized thing. So what we do here is we say set the deck as an empty list, and then for every suit in suits, remember suits, if we come back up here, that's our global variable, so we're going to be able to access it. For every suit in suits, and then for every rank in ranks, what we're going to do is, like the instructions say here, is actually append these using the card class. We'll say self.deck. So remember, that's an empty list. And then I'm going to append using the card class that we defined above. Remember, the card class just takes in a suit and a rank. We're going to pass those in as well, suit and rank. And now, after I initialize this, I should have a list of a bunch of card classes. Now for the actual string representation of this, it's really up to you how you want to represent your deck. In our case, we decided to do something like this. And remember, this function only really gets called if you actually print out your deck. So we'll start off the deck composition as an empty string. And we'll say for every card in self.deck, we're going to say that the deck composition, we're going to concatenate a new line. Let's make sure we have our quotes there. Plus the string representation of the card. So remember, card here has its own string representation, and we can call that using the following method. We can say deck composition, new line, plus card, and then string, and to actually execute it, we have open close parentheses here, which basically just calls print out the actual string representation of each individual card. So now we have this giant string with new lines, and at the end, we can just return back a string that says the deck has, and we can add in this deck composition. Then we can shuffle the deck. We actually showed it already here for you, but using that random library that we imported earlier, we just call shuffle on a list, and it will shuffle that list. Notice here, I'm not saying return. This actually happens in place. So this goes back to our discussion of object-oriented programming, where not every single method actually returns something. In this case, we're just shuffling that list in place. Finally, I want to have a deal method, which is a way to actually grab a card from my self.deck attribute, that list of card objects. So we'll say a single card is just equal to self.deck.pop. And this sort of syntax can be confusing for beginners, so I want to take a closer look at it. All we're saying here is basically two things. Grab the deck attribute of this deck class, and then pop off a card item from that list, and then set that to single card. What's confusing sometimes for beginners is that they see these two dots in a row, which is a little weird if you haven't seen it before. But in this case, it is just doing one single method off a list object, just like we did up here, where we said append off this self.deck list attribute, which is this. Once we pop off that single card, we can just return it. And technically, you didn't have to do this in 2 lines. You could have just said return self.deck.pop, but hopefully this commentary helps you understand what's actually happening here. So now we have our deck object ready to go. So let's do a little bit of testing. We should be able to create a test deck and then print out the test deck, we should then print out the deck has and this deck composition that we defined up here. So let's run this. And as you see, deck has 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts. So notice here, everything is in order. So let's do a little bit of testing by actually shuffling. So we'll say after creating the test deck, grab that test deck and shuffle it. And then instead of printing everything out in order, we should see something printed out shuffled. We run that and we see some diamonds, hearts, clubs, etc. And we can see that it's all been shuffled. So it looks like our deck class is working. All right, let's have a quick review before moving on to the next lecture of what we've done so far. At the very beginning, what we did was we set up some global variables. We also imported the random library. The global variables are a tuple to represent the suits, some ranks, which is another tuple to represent the ranks, as well as values. And this is a really important variable because it's a dictionary lookup where you just pass in the rank and you get back its numerical value so that you can easily take sums of someone's hand. Then we created a class for the card itself. So this represents just a single card, and it has 2 attributes, a suit and a rank, and you can print out a card and it will report back rank of a suit. Then for the deck class, we wanted to leverage that card class in order to quickly create 52 of every single card. To do that, we just have a nested for loop where we say for suit and suits, for rank and ranks, and by creating a empty list for this first attribute, we went ahead and took that list and appended a bunch of cards to it. Remember that card is an actual card object where we said for every suit in that global variable suits, so that's the one up here, and then for every rank in that global variable ranks, that's the one up there. We went ahead, created a card class, so now we have a card object and we appended it to that list. So self.deck is a list of these card objects. Then we wanted to be able to print out the actual deck, so if you said print deck, you'd get something. And in that case, all we do is we say, okay, start off with an empty string, and then for every card in this list of card objects, go ahead and concatenate a new line, and then the string representation of that card. And then we can print out the deck has, and it's just one giant string with a bunch of new line calls. So then when you actually print it out, you get back a list of all the cards. Then we can shuffle the deck, which is basically just calling that random.shuffle method on that self.deck list. And then we have deal, where we pop off a card object and we grab it by returning back that single card. Okay, and then we tested it out by creating a deck, shuffling it, and printing out the test deck. Coming up next, what we're going to work on is creating a hand class and then creating a chips class. We'll see you at the next lecture. Welcome back, everyone. To continue where we left off last time, we're going to create a hand class and a chips class. I want to quickly review what we did last time because we're going to be using it to actually create our hand class. Let's come back up to the very top very quickly. Remember that we have these suits, ranks, and values. These are global variables that we can easily use. And most importantly, we have this values dictionary. That means I can pass in a rank, such as 2 or 3 or 4, and immediately get back its actual value for the sum. We're going to be using that in the hand when we want to calculate the value of a hand. What we'll be able to do is pass in the actual rank of the card and then get back the value itself. After that, we actually created instances of card classes. So what that means is we basically have this card object where the card object has a suit and has a rank. That means we should, when passing in a card, grab the rank attribute and pass that into the values dictionary in order to get back an actual numerical value. Then moving on to the deck class, this was just a way to quickly create 52 unique card objects to represent each card in the actual deck. So we can see here that we used a nested for loop. So for suit and suits, for rank and ranks, we went ahead and appended these card objects where we passed in the suit and ranks. We also created a way to print them out, shuffle the deck, and then deal from the deck. Now it's time, if we scroll down here, to actually create a hand class. The hand class is basically going to represent what cards are currently in someone's hand. So the hand class, when you start off, it's going to start with an empty list, and then we're going to add cards from the deck. So we'll be, if you come up here, calling deal from the deck, and then grabbing that single card, and then adding it to someone's hand, which is what we're going to use when we call this add card method. So remember, that's going to be an actual card object. Then we have a value attribute to the hand, which is just the current sum of the value for that hand. And then we also want to keep track of aces in the hand, because recall that aces have that special rule where they can either be a 1 or an 11. So let's start with this method for adding a card. What we're going to do here is say self.cards, and then we're going to append the card that's added. So here I have an empty list, and I will say self.cards of that empty list, append the card object. So don't get confused here, the fact this is a lowercase c. Keep in mind that the card passed in is actually going to be from this deck right here, meaning we're going to call deal off of this deck in order to actually grab a single card from it. So that's what this card represents. Later on, when we're saying add card, this is going to be from the deck, and it's going to be deal. Because remember, deck.deal, that's just a single card object. And the card object itself has a suit and rank to it. So I'm going to say self.cards, append that card, and since we know that this card object has a rank to it, we're going to be able to use that rank to get the value. So how do we do this? Well, we grab that card rank. Remember, that's going to be 2, 3, king, ace. And then we pass that in to the values dictionary as a key. And that's going to return back some number representing the value for that particular card's rank. And we'll take that value and add it to our current value. So we'll say self.value plus equals values card.rank. So a lot of stuff is happening in just 2 lines of code here. We're taking in a card object that we'll eventually call from deck.deal. We're appending it to this hand's current list of cards, and then we're adjusting our value to the card that was just added to this list. We're going to take that card's rank, look it up in the values dictionary that we did at the very beginning, and then we'll add that to our self.value, which is just some number of what the current value of the hand is. And we know when self.value is greater than 21, then whoever has this hand has lost. Okay, so let's do a little bit of testing before we tackle this issue of adjusting for an ace. So I'm going to do Alt-Enter here to create a new cell below. So Alt-Enter a couple times can create a couple of cells for us. Let's say that our test deck is equal to an instance of deck. Then I'm going to shuffle the deck. So we'll say test deck, call shuffle on it. And now we're going to create a test player. So this is the human player, and we'll be using a very similar thing for the computer, where we say the test player is now represented by this hand. And the test player starts off with no cards, no values, and no aces. Then we'll say test player, and let's add a card to their hand. So to add a card to their hand, we need to grab one from this deck. So I can say that I pulled a card from the deck. So pooled card is equal to deck, whoops, it's actually equal to test deck. And then notice I can say deal. So let's break this down. We define the player, going to deal one card from the deck. Remember, that is a card object. So it's actually a card that has a suit and a rank to it. Let's go ahead and then print out that pooled card. And then once we've printed out that pooled card, I'm going to add that card to the test player's hand. So we'll say add in the pooled card there. And then let's say, what is the test player's current value? We'll say test player value. Just call that attribute. Let's run this. All right, so what happened was we created a deck, we shuffled that deck, we created a test player represented as a hand object. So that test player's hand, we got the test deck, we dealed something out, meaning we just got one single card, printed that card, so it reports back 2 of spades. Remember, each card has a string representation. And then we added that pooled card to the test player, and then we printed out the test player's value. Now we can actually do this in much fewer lines. What we can do is with that same test player right now, I'm not going to rerun this cell. I will say add a card, and inside of this, Remember the pooled card was just testDeck.deal, so I can copy that and paste it in here. And that's going to be adding another card to the test player's hand. So I run that, and now let's check our test player's current value. And now it has a 12. And now we can do this over and over again to keep adding cards to this test player's hand. However, what we still need to do is adjust for the ace. Okay, now it's time to actually tackle that issue with the aces. First off, let's take a look at our attribute self.aces. Self.aces, remember, allows us to actually keep track of the number of aces we have. So it might be a good idea that inside of this card method, what we can do is track our aces. What I will say is if the rank of that card is equal to ace, then I will say self.aces and add 1 to the count. So that means now aces is going to be 0 or some other number as I track the actual aces here. So if card is equal to ace, then self.aces plus 1. Then we need to adjust for ace. So there's two things that are going to have to happen here. We need to say while self.value is greater than 21 and self.aces, take our current value, subtract 10 from it, and then take our current number of aces and subtract an ace from it. Okay, so this is some really clever code here, which is why it's a little bit hard to read. So I want to break down what's actually happening here. We first have the check of self.value greater than 21. That makes sense because we're not going to adjust an ace to be equal to 1 unless the value is over 21. Because if we take a look at our initial values dictionary, when you first get an ace, you're going to consider it to be 11. So keep that in mind. What's going to happen is, let's come back up here. When we first get that ace, we're going to consider it to be an 11. Then, if we have that ace, we want to adjust for it. So I'll say if total value greater than 21 and I still have an ace, then change my ace to be a 1 instead of an 11. So that's the logic that we're trying to explain here. And that's what these 3 lines of code are doing. They're checking, hey, is my current value greater than 21? And self.aces. This one of and self.aces is a little bit tricky because you're using an integer as what's known as truthiness. So this means that we're actually treating this .aces integer as a Boolean value. And I want to show you what that looks like. Let's imagine that you have some number equal to 0, and then let's actually just call it 0, and then say 1 is 1, 2 is 2. If we check if these things are true or not, so if 0 print true. Notice what happens. We don't get anything printed out. So that means if 0, the actual integer, it's treated as false. So 0 has a truthiness to it where it actually is being treated as false. And other numbers that are not 0 are treated as true. So you can think of zeros or any number besides 0 is going to be printed as true. So this says if 1, print true. So it's treating the integer 1 as true. And it's going to continue for integers that are not 0. So we're able to take advantage of that in our call right here by saying and self.aces. The other way you could do this is say and self.aces greater than 0, and that's pretty much the exact same thing. The code in the notebook just says self.aces because it's a kind of clever use case, but it's the same thing to say and self.aces is greater than 0. So you can keep either version here, but all it's saying is while my value is greater than 21 and I still have aces, then take my value, subtract 10 from it, and then take my aces and subtract 1 from them. Because now I've officially switched that ace, that instead of it's an 11, it's now going to be a 1. Okay, let's rerun that and then move along to creating our chips class. Our chip class is actually going to be super simple. Basically what we do is we just have sum total of chips. And if you want, what you could do is instead of just setting the total by default to be 100, you could say self total equal to 100. It's really up to you if you want it to be supplied by a user input, so they can say I start with 1,000 chips or 5,000 chips and then set total here, or the way the notebook shows is just automatically set it equal to 100. Don't allow for people to kind of make up money for themselves. Then for the win bet, we'll imagine that if they won a bet, we will say self.total plus equal to whatever their bet was. And if they lose bet, it's the reverse. We'll say self.total minus self.bet. And that's chips, that's all it is. We just keep track of some total and the current bet that they've placed, and then we either subtract that bet if they lose it, or add that bet if they win it. Okay, so that's it for this lecture. Coming up next, we're going to define some functions that will actually help us play the game. Let's quickly review what we created so far with our hand class and our chips class. Our hand class is basically a representation of the player, either the computer dealer or the human player. They start off with cards, they have some value associated with their current hand, and then they have some count on aces. To add cards, they just pick a card from the deck, append it to their current list of cards, and then they adjust their value accordingly by looking up that card rank in the values dictionary. Then they also keep track of aces, so they do an additional check. If that card rank is equal to ace, they add an ace number to it, just count 1. Then we can adjust for ace, which means if the self.value of my hand is currently greater than 21, and I still have aces, I'm going to adjust the ace to reduce the value to be a 1, so go from 11 to 1, we subtract 10, and then subtract 1 from my ace count. And then I've done the adjustment. All right, coming up next, we're going to go along with step 6, where we write functions for actually playing the game. The chips class itself was just adding and subtracting some bet from the total. We'll see you at the next lecture. Welcome back. Now it's time to actually create the functions that we'll be using when we run the larger piece of code at the end that actually plays the game. And there's a lot of flexibility having these functions, so don't take the instructions here as the only correct way to do this. We're going to start off by creating a function called takeBet that is going to ask the user for a bet and then set that as the actual bet. So let's do the following here. We'll say takeBet, and we'll pass in some chips, and then we will say while true, we're going to try the following. We'll say chips.bet is equal to the integer of the input. How many chips would you like to bet? Question mark, space. And then we'll say except, so if they didn't actually input an integer, maybe they put in a letter, we'll say print, sorry, please provide an integer. Then we can say else if chips.bet is greater than the total number of chips available in this object, you'll say print, sorry, you do not have enough chips. You have, and then we can insert how much they have. So we'll say dot format chips, total number of chips there. Else, we're going to break out of this while loop. So this is just one way we could have done this. You didn't actually have to pass in the chips here. There's an example in the notebook, which I'm going to drag over real quick, just so we can see it. Here we can see that there's another method you could have done this that would not have taken in the chips object. Instead, if you knew in advance that you were going to call a particular player's chips object, you could have just called player chips here .bet. So it's really up to you depending on how you can call this function, whether you want to pass in any arguments or not. Usually when you're calling a function, you're going to want to pass in arguments. That way you can have control of the global variables without needing to call that global keyword. Again, it's really up to you, whichever version you prefer. So we'll go with the version that we have where we're actually asking for the chips. So let's break this down what we just did. We take in some chips. Remember, that's the class we just said here, and it has a total and a bet attribute. We set the bet equal to whatever the player wants to bet. we say except if they're not providing an integer, and then we do a quick little check that even if they did provide an integer, we want to make sure that the bet is not greater than the chips total. And if that's the case, we'll print out a little message telling them how much they have left. Else, if that's okay and there's an integer there, we'll just break out of this while true loop, and we've set chips.bet successfully. So let's run this and now move on to step 7, which is to write a function for taking hits. This one's actually pretty straightforward. All we need to do here is say hand, and we're going to add a card to the hand from the actual deck. You could do this all in one line, or you could separate it out into 2 lines, saying something like single card is equal to deck deal, and then add in to that hand the single card you just defined. And we want to make sure that we adjust for the ace afterward. So we can say hand adjust for ace, and we'll call that method as well. All right, so now we have hit. It takes the deck and someone's hand, grabs a single card from the deck, adds it to the hand, and then checks for an ace adjustment. Step 8 is to write a function prompting the player to hit or stand. So this function, what it's going to do is going to accept the deck and the player's hand as arguments and assign playing as a global variable. And this is actually to control an upcoming while loop. You could just provide playing here in the function as well and then return it back. It's kind of up to you how you want to deal with it. But this is just going to be another while true loop, very similar to before. We will say x is equal to input, asking hit or stand, enter h or s. And then we'll say if x lowercase is equal to h. So why am I doing this? Well, maybe someone is going to misunderstand this line and then type out something like hit or something like hh. Maybe they do lowercase stand. In that case, what I'm going to do is be able to grab the string, grab the first letter of it, lowercase, and say if it equals h, they probably meant to hit. So I'm going to say hit from the deck on their hand, else if x0 dot lowercase is equal to s, I'm going to assume they want it to stand. Now I'm going to say print player stands, dealer's turn. And I'll set playing equal to false. And this is because I'm going to use this in a while loop later on. You didn't have to do it this way. Again, there's many different ways you can control the while loop later on. This is just the way we're going to do it so that we can kind of clearly see it in the while loop later on. Finally, we'll have an else statement that says print, sorry, I did not understand that. Please enter H or S only. Because that basically means they didn't enter something that starts with an H or an S. Then I'm going to continue. And if none of those gets triggered, then what happens is we just go ahead and break. All right, now for step 9, we want to write functions to display cards. And you notice the instructions basically are going to ask you for 2 functions, the show sum and show all functions. So when the game starts, and after each player takes a card, the dealer's first card is hidden, and all of the player's cards are visible. Which means what we want to do is have 2 situations. One situation where we're just showing that dealer's first card and all of the player's cards, and then the second situation where we're showing all the cards, both for the dealer and the player. So we're going to have 2 functions. First one's going to be called show sum, and it takes in both the player and the dealer. And so the objective here is to essentially show only one of the dealer's hands, or I should say dealer cards from their hand. And then here we're going to show all, which at the start of the game should just be 2 cards of the player's hand, or cards, depending on how you want to phrase that. But basically all I'm saying is this function is just going to be for the very start of the face-off, so to speak, where both the dealer and the player have 2 cards, and the dealer is just showing one face up and the other one is showing face down. Then we're going to have another situation that at the end where you see who wins, if it's a push, if it's a loss, we want to have some sort of show all function. Again, takes in the player and the dealer. And this one's much simpler. It's just going to say show all the dealer's cards. And then also show all the player's cards. Now in this second one, because ideally this is being done towards the end, whoops, here we go. Ideally, def show all, this is technically being done at the end when you want to calculate who won the match or who busted, etc. So not just showing all the cards will be important, but also displaying the value for both. So we're also going to want to calculate and display the value. And what I mean by value is if they have, for instance, a jack and a king, I want to actually show you that that equals 20. So I'll say, okay, here are the dealer's cards, jack and king, and that equals 20. And recall that the dealer actually has an attribute called .value, which is going to allow us to just quickly grab that value. But let's start off with show sum. So I want to first show the dealer's cards. So what I'm going to say is I'm going to print, and we're going to say print a new line, and then say dealer's cards, or dealer's hand, really. And be careful here with the quotes. Notice how I have double quotes on the outside and just a single quote on the inside. That way I don't prematurely end this string. And then we're going to print, we're going to say first card hidden. Because you don't get to see one of the dealer's cards. That's kind of what gives them an advantage. And then what we're also going to do is then print the dealer's cards. So we just want to print one of them. And recall at the very start of this match, the dealer has 2 cards, which means from a object-oriented programming perspective, we can think of we have this dealer passed into the function, and then they have the attribute cards. And there's 2 cards. There's going to be the list index 0, which is the first card, technically hidden, and then the second one, cards 1. So we're going to show cards 1 here. So we're going to say print, and then what I'm going to say is print dealer.cards1. So what is that actually doing? All it's saying is don't show the card at the first index at 0 at the start of the match. That's kind of what we're saying here, first card hidden. And then we're going to show the dealer.cards1, essentially the second card. And then we need to show all of the player's cards, which is going to be 2 cards. So how do we do this? Lots of different ways you can do this. I think probably the simplest way to wrap your head around this is to just do a for loop through all of the player cards. So you can say for card in player.cards. Recall .cards is a list. That's how I'm able to index it up here. So for card in player cards, I can just say print and then say card. And I should probably have an announcement before this starts printing that this is going to be now the player's hand. So we're going to start a new line here and then say player's hand. So all this is doing is it's going to say, hey, first card is hidden. This can technically be a string that says whatever you want. And then it's going to show that second item in the dealer list. And then this one's going to say, hey, print player's hand for card in player.cards. Go ahead and print that card. So this shows one of the other cards and shows all of the 2 of the player's hands. And now for show all, essentially what we're going to do is kind of copy and paste what we did here. So we know now we're going to do this same logic. I'm going to copy this, and I'm going to paste it here for showing all the player cards. Let me just tab this over to get correct indentation. There we go. So we're going to show all the players' cards, and it's going to be the exact same code for the dealer's hands or cards. So paste that in as well, except now I'm going to change this to say dealer. So dealer's hand, and then dealer cards. So for card in dealer cards, go ahead and print that card. In the same way for card in players.cards, go ahead and print that card. But remember, I wanted to also calculate and display the value. So luckily for us, we can easily do the following. I can say print, and then say, for example, value of dealer's hand is, and then we can use f-string literal formatting to put this in. So there's a lot of different ways we could do this, but one way is recall from our string formatting lecture, I can put an F at the front of this, and then in curly braces, I can pass in any Python variable I want. And so I could pass in dealer.value. So that's one way of doing this. I could also then have the .format method, if you recall. I could have passed in .format and then left this blank, put that in here, etc. If you're confused on that at all, go ahead and check out the string formatting lecture again, but lots of different ways. You can just essentially paste in the dealer value. And all you need to do is the exact same thing for the player. So after this for loop is done, check my indentation here. Notice how the print is in line with the for. I don't want to keep printing the dealer's hand value over and over again. So I'm going to do the same thing here, except this time it's for the player. So we're going to say player's hand is, I'm going to call this player.value. And really, that's pretty much it. So again, all we're doing here is showing on the first one, just one of those cards, show all the players' cards, and then using the same logic, we just loop through all the dealer's cards, print them all, and same here, loop through all the players' cards, deal them all, and show them all. And then, luckily for us, we have that quick calculation of the value as an actual attribute. Now, there are some kind of more savvy ways to do this, and one way is to use an asterisk. And an asterisk symbol is used to print every item in a collection. And it's kind of the special use case that you can use for when you have something like this and you don't want to actually write a for loop. So let me show you what that can look like. Again, don't worry if you didn't think about doing it this way. It's just a little quick note. And we do post this in the solutions notebook so you can check it out on your own time. But for example, another kind of faster way I can write this exact same command, print dealer's hands and then loop through dealer.cards, is to say print, and then here I can say whatever I want, such as \n dealer's hand. So that code stays the same, but this loop I can actually then say the following. I can say comma, an asterisk, and then say dealer.cards. And so what that is going to do is it's essentially going to loop through every item, and then it will also print it out. And then depending if you want this all done on one line or multiple lines, you can add in a third argument called SCP for separator, and then pass in \n to say, go ahead and put in a new line every time you show and print out one of these dealer cards. So keep in mind, this is kind of a third option you can do. And let me just quickly walk you through an example of this by creating a cell up here, just so you can get an idea of what that logic looks like. So I'm going to create 2 new cells, and let me just make a list of items that looks like 1, 2, 3. So I could say for, let's say, card in items, print card, and that's kind of the logic we were already going for. And if you were to do something like that, you see 1, 2, 3. Or what you could do is the following. You can say print, and then if you want, you could have it blank or have some sort of statement such as items are colon. So items are colon, comma, and then say an asterisk there, and then items. And note what's going to happen here. It's going to say print. It's going to loop through every single item in this list, and then say items are 1, 2, 3. If you want these all on new lines, you can say separator, and then \n. Run that, and you can see items are 1, 2, 3. So that's the way this logic works. It's essentially just some functionality that's put inside of the print function, because doing something like this is actually really common in Python. There are going to be lots of instances where you're going to end up printing every single item in a list. So you don't have to do that for loop. They have that special kind of asterisk looping through things. And you'll actually see this come about again when we talk about args and keyword arguments, or kwargs. So just keep this little idea in mind. You're going to see it pop up again later. All right, let's move on to step 10. Okay, the next thing we want to do is write functions to handle each of the game situations where it's going to end. And remember to pass in the player's hand, the dealer's hand, and the chips as needed. So let's go ahead and pass those in. We'll say pass in the player, who's represented by a hand. Let's make sure we spell that right. Pass in the dealer, who's represented by a hand object, and then pass in the chips themselves. We'll grab these and pass them into all of them, except for push, because if there's a push, that means both player and dealer got 21. So we won't actually do anything with the chips. So here on push, that's the easiest one. We don't really do anything. We just say dealer and player tie, push. For the other ones, we're basically going to print a message out and then adjust the chips themselves. So if the player bus, we'll print out bust player. We'll take those chips, and then we'll call the lose bet method off of them. Player wins, very similar thing. we print out player wins. We take those chips, and then we say win bet. If the dealer bus, it's going to be the same thing up here. The player will win the dealer bus, except we'll add another message here. Player wins, dealer busted. If the dealer wins, it's going to be a similar thing to the player busting, except the message will be different. They'll still lose their bet, except we'll say dealer wins. Okay, run that cell. And now, the last thing we need to do is actually run the logic of the game. We'll be doing that in the next lecture, but let's quickly review what we did in this lecture. So we started off by creating the actual functions that we're going to be calling in the next lecture. We first start off with take bet, which is just in some form or manner getting an input from the user and then setting it to the current bet. Lots of different ways you could do this. Then we wanted to write a function for taking hits. So we take in the deck, we take in a hand, we take in a single card from the deck, add it to the hand, and then adjust the hand for an ace. Then we wanted to write a function prompting the player to hit or stand. Basically, we just wanted to figure out, hey, am I going to call hit, or am I going to just stand and say that this current player is no longer playing, or it can just continue if they didn't provide an H or an S. Then I wanted to write functions to display the cards. Lots of different ways you can do this. You can check out the notebook for some more advanced one-liner ways of displaying all of this information. And then we wanted to write functions to handle each of the game situations where we basically either call lose bet or win bet and print out a message. Coming up next, we're going to code out the logic for the entire game. All right, let's get started with actually programming out the game. We're going to print some opening statement. In this case, we'll just do something simple like welcome to blackjack. And then we want to create and shuffle the deck. So we'll say deck is equal to an instance of a deck object. And then we'll grab that deck and we will shuffle it. After that, we want to set up the players themselves. So set up 2 hands for each player. Or I should say a hand per player, hand per dealer. So player hand is equal to an instance of the hand, and we're going to grab that player hand and then add a card to it. And the card itself is going to be just dealing from that deck. So we'll say deck.deal. And we're going to do this twice. And we'll actually do a very similar thing for the dealer. So we're going to copy and paste this code, except instead of the player hand, it will be the dealer hand. So we'll say dealer, create a hand, add a card to this twice. So we created a deck, and now we have a player hand and a dealer hand. Up next is to set up the player's trips. So for this, we'll say player chips is equal to a chips object. Remember, the default value is 100, but you could adjust this depending on how you define the actual chips object above. Then up next, we want to prompt the player for their bet. So we already have the take bet function that does this for us. We say take bet, and we're going to pass in the player's chips. And then we want to show cards. So in this case, this is still the beginning of the game, so we'll only call the show sum function. We'll say show sum, and then we'll pass in the player hand, the dealer hand, and then we'll also pass in, actually that's all we need to pass in for show sum. And then while playing, recall this variable from our hit or stand functions. This is a global variable here. So while we're playing, we're going to ask the player, do they want to hit or stand? So we actually have this hit or stand that takes in the deck we created, as well as the player hand. Then we want to show the cards. Since the player is still playing, we're going to say show sum again. And it's actually the same here as above, show the player hand and the dealer hand. So we'll copy this and paste it in. Then if the player's hand exceeds 21, we're going to check or run player bus. So we'll say if the player hand, I should say the value of the player hand, remember that's an attribute. If it's greater than 21, then this player has busted and they've lost. So we will call player bus and then pass in the needed information, including the player hand, the dealer hand, and then the player chips. After that, we can just break. So let's go over what we've done so far. We've set up the deck, we set up the player's hand, and we set up the dealer's hand. We set up the player's chips, we've taken a bet from the player, and then we show some of the cards. Basically, show some means still show that dealer's hand as one of the cards face down. Then while playing, we will say hit or stand for that player. We'll show some of the cards. Let's make sure that lines up there. And then if that player's hand value is greater than 21, we're going to bust out of that. Now for the next step, we want to check if the player hasn't busted. We're going to play the dealer's hand until the dealer reaches 17. And I'm going to explain that in just a second, but let's write out the code for it. We'll say if the player hand value is less than or equal to 21, that means the player hasn't busted. And we're going to say while the dealer hand value is less than 17, go ahead and hit using the deck and the dealer hand. Something I want to note is it depends on how you want to set up your game, whether or not you want to use the value of 17 here. If you're familiar with the game of blackjack, in a casino they have this rule called soft 17, that the dealer only hits until they reach 17. Now, the way you could have also structured it is say, while dealer hand value is less than the player hand value to keep on hitting. It's up to you whether you want to do this soft 17 rule, or if you want to just keep going until you either beat the player or bust. So either one of those methods is okay. Again, it really depends on how much into detail of the game of blackjack you want to go into. Right now, we're really just focused on coding, so either one of the options is fine. So since the dealer is now playing, we need to show all the dealer cards. We will say show all, and we'll say player hand and the dealer hand. And I'm just using tab to autocomplete there. Then we run the different situations where someone may win or lose. So if the dealer's hand value is greater than 21, then the dealer has busted. So we say dealer busts, and we pass in the player hand, the dealer hand, and the player's chips. If the dealer hand value is greater than the player hand value, then the dealer has won. So we'll say dealer wins, and then we pass in the same three parameters as before. So let's copy that and paste them in. Else if we have another situation to check, so we'll say if the dealer hand value is less than the player hand value, and this is more dependent on that soft 17 rule, because it kind of depends if you initiated this as 17, then this situation may come up. If you just keep going until you bust, then this situation won't ever come up. But we'll still pass it in here, so we match up the notes. We'll say player wins if the dealer hand value is less than the player hand value. And again, we just pass in the player hand, the dealer hand, and the player chips. Else, and then finally we check the situation for a push where they both happen to get 21 and they tied up. We'll say push on the player hand and the dealer hand, which are the functions we defined before. Then we want to inform the player of their remaining chips, so we're going to say print. We'll say print a new line just so we get some space here. Players total chips are at, and we'll end the string there and format in player chips total attribute. And then finally, we'll just have some little small loop here to ask them if they want to play again. So we'll say new game is equal to input. Would you like to play another hand? We'll say yes or no. And if the result of the new game, if that first letter, let's say if that first letter lowercase is equal to a Y, we'll set playing equal to true, and then it's the player's turn again, and we'll continue along. Else, what we're going to do is say print, thank you for playing, and then we'll break out of that entire loop. Okay, so we just did a lot of code here, so let's zoom out and run through all the steps here, and then we'll debug just in case we have any typos. So, the game. We say while true, we print out welcome to blackjack. This is the pretty straightforward stuff. We create a deck, we shuffle it, then we create a hand object to represent the player, add 2 cards to that hand. Then we create a hand object to represent the dealer's hand, add 2 cards to that dealer's hand. We set up the player's chips, then we take a bet from the player, and then we show some of the cards. So we say player hand and dealer hand, and show some means that the dealer's hand is still hidden. Then we have this global variable called playing. And while we're still playing, that is the human player is still playing, we ask them if they want to hit or stand. Then we show some of the cards, so the dealer's card is still hidden. And then we check, did the player bust or not? If they busted, then we just break out of this. If the player hasn't busted, that means their value is still less than or equal to 21. We check while the dealer hand value, and you can say either less than the player hand value or less than 17, depending on how you actually want to implement that rule, you'll keep hitting. Then you're going to show all the cards, and then you'll check for the different situations. Either the dealer's busting, the dealer wins, the player wins, or it's a push. We inform the player what their total chips are, we ask them if they want to play again, and then we have this little loop that will either reset the playing to true or we'll break out of this while loop. Let's run this and see if we get any errors. Okay, how many chips would I like to bet? First off, let's bet way too many chips and see if we get that error. So it says, sorry, you don't have enough chips, you have 100. Okay, so far so good. Let's bet 50 chips. Dealer hand, we get 1 card hidden, and they have the 10 of hearts. I have the Queen of Hearts and the Queen of Spades. Remember, that total value is 20, because that's 10 plus 10, so I'm definitely going to stand. I'm going to enter S here. So I stood, and then I have dealer's hand, Ace of Hearts, 10 of Hearts. So that's a straight 21. That's pretty freaking lucky. But looks like we lost even with a great hand of 20. So I have total chips are 50. Do I want to play another hand? Yeah, let's do it. Let's see how good our luck is. Welcome to Blackjack. How many chips would you like to bet? Let's see if I bet 100 again, what happens? So notice if I bet 100, I actually don't get an error because it's being reset the way we designed it. So I'm going to scroll up real quick just to show you this. So each time you call chips here, it's being reset because of the way we define chips. All the way back up here, we said by default the total is equal to 100. What we could have done is kept going with some sort of recurring chips object and not have it reset 100. It's up to you how you want to think about this, but you could assign chips instead to maybe a player. So let's continue along. We basically reset our number of chips. We'll come back down here and let's check what we have. Player's hand is an 18. I'm going to stand again. That's a pretty good hand to stand on. And we have dealer's hand was a 2, 6 of clubs, and an ace of diamonds, so that's 19. Dealer wins again. Player chips total. Let's say, yes, I want to play again. And I'm going to just put in a bet here. 1 card hidden, 10 of diamonds. I have 5 of diamonds, Queen of Hearts. So I can tell this game is definitely favored towards the dealer. Let's hit just so we can practice hitting. And now I have 5, 10, and ace, so that's 16. That's pretty lucky. We'll stand there. And let's scroll all the way down. You'll notice in Jupyter Notebook if you have too much. So it looks like the dealer ended up busting, so we won. So the dealer hand was too much. It kept going, and now we are at 120. Would I like to play another hand? No, thank you. Say no, and now it's thank you for playing. Okay, that's it for the entire game. That's definitely a lot of code. And keep in mind, your solution could look way different than this. There's basically an infinite number of ways you could have programmed out this game. You could have made more classes, used more functions, assigned maybe a player class and a dealer class instead of just hands for them both. So it's really up to you, the flexibility here. If you have any questions, feel free to post the Q&A forums. But this basically concludes the second Milestone project. We'll see you at the next lecture.